semi-supervised learning, and that's because what we've got here is each of these circles represents a build. The green ones are builds that we think are fine, the red ones we think are not fine, and the black dots represent builds where we weren't able to conduct any certification. So the idea is that you can get a better picture of these clusters if you combine the coloured dots with the black dots, if you just have the coloured dots on their own. So this is an example how a bit of industry pull has led us into kind of semi-supervised machine learning. The group was then joined by Serini, who's on the bottom left, who's just writing her PhD thesis now. So she took it to the next level and started to predict build density from features of photodiode measurements. So this diagram shows outputs of a Gaussian process, which is one of our favourite tools, predicting build density. And the key thing here is that all the predictions have confidence bounds. So in my opinion, if we're going to do machine learning and we're going to use it to make a difference in engineering, then uncertainty quantification has to be built into it from the very beginning, because what we've got is data-based algorithms that potentially can influence high consequence decisions. So this could be used to decide whether or not a part should be used in an aircraft, etc., etc. So a fundamental academic challenge in all of our work is to make sure uncertainty is properly addressed in all of these approaches. She then took this even further and has now gone down to the resolution of predicting essentially the grayscale of CT scan images, which is quite exciting. So on the left here we have a CT scan of a layer of a laser powder bed fusion build, and some defects have deliberately been introduced into it. And on the right, we have our machine learning algorithms prediction of what that CT scan was going to look like. So currently, hopefully this is going to be developed into a box which is going to sit on top of a laser powder bed fusion machine, and it'll flash red if something goes wrong, in which case you can stop the build or take some kind of corrective actions. But as I said, uncertainty quantification is absolutely the heart of all this stuff, because the algorithms kind of informing us as to the quality of the build of a metal component. So still in manufacturing, we've done a lot about continuous processes, and unfortunately I don't have any cool pictures here because we're a little bit restricted on what we can show, but let's say you have a continuous manufacturing process. It's like a production line that's, say, creating paper or glass, that kind of thing. And particularly we focus on high value and bespoke products. So bespoke's quite important here because it means these production lines have to change to adapt to changes in customer demand. So if the demand requirements change, then they have to change parameters of this process, so temperature and humidity or whatever, that kind of thing. And then while that process settles back down to its steady state, while they're trying to find the correct parameters, potentially everything that's produced during that time is wasted. So this is a fun machine learning challenge because you have sensors all over your production line, but what you want to do is predict what's going to happen into the future. So you kind of want to predict what the quality of this product potentially 8 hours into the future. So there's kind of two ways you can do this. Either you can try and do it directly. So I've got here some sensor measurements that I've written as X. We've got a bunch of them at time t. We want to know what happens at time t plus k, so that could be 8 hours later. And so you just try and map directly from your xt to your yt plus k, where y is the quality of your product, that kind of thing. Or you can try something called an autoregressive model, which I'm sure you dynamicists have encountered many, many times before. But basically what we're going to do is we take our sensor measurements, so xt, but also, let's say, the quality of the product at time yt. And that yt is also used as an input into the model to predict the product quality at t plus 1. So we go one step into the future. And then if we want to know what happens at t plus 2, now that previous prediction, yt plus 1, is an input into our model. And so by doing this through this autoregressive framework, you can step by step move your model further and further into the future. So it's kind of more flexible because you're not fixed on how far into the future you're trying to predict. The academic stuff, where it gets quite interesting, well, more interesting, is that if you're doing uncertainty quantification, your yt+1 is uncertain as your previous prediction. So now you've got an uncertain input into your model to get yt+2. So these are my only equations, I promise. You end up with this kind of situation where you say, okay, our yt+1 has come from some kind of probability distribution. Fine. If we now want to predict at yt+2, we have to integrate over all the yt+1s because they're uncertain. And so this can be a right mess. Basically, if you've got a Gaussian process, for example, then your PDF over yt+1 is Gaussian. And it means that your PDF over yt+2 is an infinite mixture of equally weighted Gaussians. So it's already a bit of a disaster. And that's only in yt+2. So the kind of fundamental challenge here is we're actually trying to deal with really messy probability distributions that we don't have convenient closed form solutions for. And just to note that there's a really interesting thesis down here written in 2004 that goes into approximation schemes. I think it was pretty much, it's best of my knowledge, I think it was the first one to do this, approximation schemes for autoregressive Gaussian processes. And it has cool pictures like this that show a model being used to predict into the future, and the confidence bounds are growing as a result. And so you would see how far you can push it, basically, until your confidence bounds become unreasonable. And then you say, okay, that's as far as we can look ahead in our manufacturing process. It's pretty similar for helicopters. So we have a flight simulator at Liverpool for simulating rotorcraft. Rotorcraft dynamics are pretty hard, as I'm sure you can imagine. It's non-linear, all closely coupled. There's a lot of stuff that's spinning, technical term. And in these flight simulators, at the heart of all these flight simulators is a model that's predicting the response of the aircraft, rotorcraft, I should say. And these things have to run in real time. So that requirement to run in real time leads to a lot of simplifications being made to those models. And so as a result, you might lose model fidelity. And in the worst case scenario, you might then, if these flight simulators have been used for mission rehearsal, et cetera, you might actually be delivering quite poor or counterproductive training to pilots. So this is a picture from the PhD done by Ryan Jackson, who's down the bottom here, who I think is on this call somewhere. Now works at United Utilities doing data stuff. So this is from his PhD thesis. And these coloured bands show two different machine learning algorithms that are trying to predict the pitch rate of a helicopter in response to the pilot moving the stick, basically. And they're relatively close to this black line, so blue dashed line, which is the real response of the helicopter. And the black dashed line shows the model that would have been used in the flight simulator. This is actually an autoregressive model as well, so we hit the same issue as with our process manufacturing. We've had to use quite a long Monte Carlo simulation to build up a picture of the uncertainty in our predictions, and we can't do that in real time, obviously. So again, the challenge here is we've got tricky PDFs that we have to deal with somehow and approximate quickly for the model. There's also potentially huge data sets involved as well, possibly data from entire flight campaigns. Okay, and some structural dynamics. So this is an example that came from the University of Southampton. We've got a dynamical system that we want to model. So this is actually an energy harvester. So it's mounted on a shaker table. And we have a mass in the center that oscillates up and down. And via a ball screw, that translational motion gets converted into rotational motion. And it's then connected to an electric motor at the top. So that's how it's translating kinetic energy into electric energy. So we can shake this system around. We can measure the acceleration of this mass. Excuse me. We've also, we've had a go at writing down a model, and it's got some parameters, theta, so they could be, damping terms, friction terms, that sort of thing. We want to realize a probabilistic estimate for theta. And so this is quite a common example where we write down Bayes' theorem. It gives us a non-standard probability distribution over theta, those model parameters, and we have to deal with that somehow. So typically you might use some kind of approximation scheme, or you might try and sample from it. So one of the most popular ways of doing that is with an approach called Markov chain Monte Carlo, or MCMC, which is like a generic sampling algorithm. So we did some work with EDF for a while, modeling bits of nuclear power station. And a key thing for them, which was really interesting, which I didn't appreciate initially, was they really needed to show that they'd done everything they could to make this model as accurate as possible. So specifically, they needed to show that they'd used enough data. It's because of these models we're going to go on to influence a high consequence decision. It's very important that they can demonstrate that they did everything correctly. They used enough data in training. So this, again, that's kind of an example of how this industrial pull led us to develop a kind of sampling approach that lets us track how our parameter estimates converge and how our confidence bounds in those parameter estimates kind of close in as we analyze more data. So I think this is kind of the first thing I wrote when I got to Liverpool, and here it is applied to the system from Southampton. We've got 3 different parameters. These are all parts of friction, because friction is really hard. Hard to measure those parameters directly often. And on the x-axis is time. So what we're doing here is we're analysing a time history of the dynamical response of this system, and about this time index kind of 400-ish is where friction really kicked in. It got stuck briefly, and suddenly all our parameters start to converge. And so we tried to find an efficient way of getting these plots. And like I said, it's to address those issues like, have we used enough data? How can we demonstrate that we can really trust this particular model? So I've gone through quite quickly those applications. So then we kind of look back at those, and the idea is we try and extract from them, what's the really difficult challenges that are at the heart of all these. And we spend a lot of time trying to deal with difficult probability distributions, basically. So the clustering problem right at the beginning, we're trying to approximate things with a mixture of Gaussian distributions. So CT scans, they were predicted using a Gaussian process. If you decide that you want your measurement noise to be a function of your input, or you want to use it for classification, or you want it to be non-stationary, then straight away it throws up non-standard probability distributions. Our autoregressive models were very quickly giving us non-standard distributions that we have to approximate. And so what you tend to see these days in a lot of machine learning stuff are these approximate inference schemes. So a classic is the Laplace approximation, where you essentially fit a Gaussian to the thing, you find the highest point, you fit a Gaussian to it. There's a lot of really interesting stuff around variational Bayes, where you don't always, but a lot of the time, you hypothesize that the distribution you're trying to approximate, you would say your parameters of your probability of parameter 1 and parameter 2 are independent, and you kind of use that approximation, that hypothesis to build an approximation. So you don't hypothesize a specific family, but you have to hypothesize something else. And then expectation propagation is really interesting. That's where you write down Bayes' theorem, and for the cases where your likelihood is a product of lots of independent terms, you kind of sweep through them all. You try to realize approximations to each one as you go, and you can go back and try and correct ones that have gone a bit wrong. For example, if they have negative variance and that sort of thing. And there's a lot of that stuff out there, and it's really, really clever, and it's really elegant. But I think fundamentally, we wouldn't need it if we could just sample from these awkward probability distributions. like I say, Markov chain Monte Carlo is the kind of the standard way we approach this, but it's kind of in general, it's not very good you can't parallelize it very easily, basically. By definition, you grow Markov chains, and so what it does next depends on what it did before. So they're not particularly well suited at fully exploiting highly parallel computing architectures. So one of the main things we try and do now is we've got into something called sequential Monte Carlo samplers, which is an alternative to MCMC, which is much better suited to highly parallel computing architectures. And that's something we're pushing quite hard now, because potentially we might not have to rely on all these approximation schemes so much anymore. It's got some parameters to tune that MCMC doesn't have. So the stage we've got to at the moment, this paper that we released, I think about a month ago, is basically we've found a way to tune one of them. Not to devalue that work too much, but basically we've got for example here, this red line is our algorithm properly tuned, converging quicker than this black line when it's not properly tuned. So that's one of the kind of fundamental academic bits of research that have come out from this kind of industry pool. And the other one was, it shouldn't have been, but it was a bit of a surprise, and was just education. So I kind of started to realise, and I could be completely wrong about this, to be fair. I started to realise that a lot of these problems could be solved using existing techniques. It's just that knowledge hadn't transferred out of universities and into basically the real world. And it's not really a criticism on anyone's part. The way we have to write papers, they're not the friendliest things that you'll ever read most of the time. Likewise, if you're working, you're trying to keep a company afloat, you don't have time to investigate an algorithm for 2 months to realize that you don't need it. And actually that education, the transfer of knowledge from universities to industry, I started to realize was more and more important, and I devote more and more time to it. Obviously we still need the fundamental academic research, but I now see one of the most important things that I can try and do as a lecturer is act as someone that can translate this stuff. And that's one of the ways that we can really sort of deliver change. And it's led to a load of kind of weird experiments to try and make this happen, including tutorials, and I was trying to think of some of the ones that didn't work very well. I started a Twitter account that was supposed to help with this, but I just use it to talk about cats. One of the things that has really helped is we've started to publish our code. Should have done this, realistically, for years. We never did. I know computer scientists do this more. I think engineers perhaps less so. So our most recent paper, we published all the code, and we've got a framework for if people want to collaborate. It's a bit scary because you might have got it wrong, but it's if you believe in the work, I think it's what we should be doing. Got invited to write a magazine article, which was quite fun. But one of the things I've really enjoyed is during the lockdown, when I was bored, I started making YouTube videos, and it's been really surprising. It's led to, I think, at least 2 projects, because someone has also been on lockdown and bored, watched them, and thought, oh, actually, I think I understand now what machine learning might be able to do for my, my particular problem. Well as just seeing, just diving straight into a deep learning paper, perhaps that's, not so obvious just because of the way those things are written. So it's a really interesting outcome, this education element. And then talking next will be Diego, who's, again, one of the challenges we identified is dealing with noise that isn't Gaussian, because that's an assumption that we often make. So that's something that Diego will be talking about. And that's that. Thank you very much.
Thank you very much, Pete. That was really great, and I really encourage everyone attending this talk now and then later afterwards to actually look at the videos online, which are really amazing. And actually, thanks to one of them, I had an idea that then